Hello, continuing with our work in equations of tangents and increasing and decreasing functions, we're going to look at our two examples here. So we know already that if dy dx is positive in a particular region, that means the function would be increasing. The slope of the tangent to the curve, so the slope of the curve is positive. That means that the function is rising, is going upward. That's what it means to have our positive slope. And if dy dx was negative, it would mean the function was decreasing. Now let's use that knowledge in practice. Over what interval is f of x equal to this increasing? What does that question mean in practice? I am looking for the interval where f dash x, I'm using function notation, so f dash x is greater than 0. Increasing is going to mean that the derivative is greater than 0. I'm looking for where I have a positive slope. So let's find out. I have my function here, so f dash of x multiply by the power and subtract 1 from the power. I want to know where that is greater than 0. So that is what I'm after. So I now recognize that I just have a quadratic inequality and I'm effectively trying to solve it. And then I'm going to use a sketch to figure out my bounds of my graph. Now, what do I recognize when I'm trying to factorize this? Well, if it was a normal quadratic, I'd be using the minus b formula, or I would be trying to factorize it out. But this is a little bit different. I don't have an x term here. But what type of factorization should I always try first? I should always try common factor first. So common factor comes first. If I take out a common factor, or I can see I have a common factor of 3. So if I take out a common factor of 3, I have x squared minus 16 is greater than 0. Now I don't care about my factor of 3 here. I can divide both sides of that and not lose any information. I shouldn't divide out any equation by x's because I would be losing information about the question. I'd be losing possible results, but I should always be able to divide out by constants and not affect things. And because I'm dividing by a positive constant here, I don't need to switch around my sign. Now this is fairly straightforward. I should be able to recognize that this is a difference of two squares, a dots type situation. So I rewrite this as x squared minus 4 squared is greater than 0. If I want to find where this is true, I'm going to turn it into an equation. 4x on x plus 4 is equal to 0. And I'm going to break that up, and I have x minus 4 is equal to 0, or x plus 4 is equal to 0. So I end up with x is equal to 4 and x is equal to minus 4 are the two roots of my equation. But I need to know what the interval is. So I'm going to draw a sketch to help me keep track of what it is I need to know. So I have a positive quadratic, which is going to be a smiley face type function, and I know that it has roots of x is equal to minus 4 and x is equal to plus 4. So what do I know about this function? I know that if we're crossing the x-axis, my roots are minus 4 and that plus 4. So if I know that, then I'm looking for where this function is greater than 0. Well, that's going to be when my y outputs will be greater than 0. That's going to be down here. My blue line is going to be above the x-axis, going to have positive y values for any x less than minus 4. And for any x greater than 4, my blue line is also above the x-axis. I get positive y values. If I pick, say, x is equal to 5, I get a positive y value, a positive y coordinate. So anything where x is less than -4 and x is greater than 4 will give me the answer that I want. And I can combine them if I'm comfortable writing it. I will get full marks for this, but it's important we be able to read these things as well. So x being less than -4 and x being greater than 4. And that's the way that we could write our interval, but this way is fine as well. Now let's have a look at our second situation. Show that this is increasing for all values of x element or. Well, x element or means the real numbers, so it's any number from -infinity up to +infinity. We don't mind what number we put in. So what are we really being asked? Show that it is always increasing. Well, translating that into maths then, if I call that y, so I want to show that dy dx is greater than 0 for all values of x. Remember that the upside down capital A is our for all. So this is really what this question is asking. So let's find dy dx and see if we can show that it is always going to be greater than 0. So, yeah, we'll find dy dx and then we're going to discuss what this question is similar to. Or we'll do it now. Now, if we're looking for something always being greater than 0 for all values of x, we've already done this type of question. So the dy dx part isn't the most important. Showing that something is always greater than 0. How do we show that something is always greater than 0? Well, the part that changes, the variable, is going to have to be squared. Because if we have a real number squared, it's always going to be positive or 0. So what we really want to show then is that we can write our variables inside of a square. Because if something is squared, it cannot be negative. So if we can get our derivative and then factorize it so that it has all of its variables inside of a square, that means we'll be able to show that it's always positive. And this is the general method for any time we're asked to show that something is greater than 0 or greater than or equal to 0. So it's important anytime we're looking for something always being greater than 0 or always greater than or equal to 0 or always positive is another way they could say it. It is important that we're able to keep track of that. So we are going to complete the square in order to do that. That's the most common method that we end up using. So let's look at this in practice. Let's get dy dx. So y is equal to 2x cubed minus 12x squared plus 30x minus 5. We know we want dy dx because we're looking for that the function is always increasing, therefore, or the slope must always be positive. 6x squared minus 24x plus 30. And we want to know that this is always greater than 0. And again, the method we are always going to use for this, or almost always going to use for this, is to get stuff inside the bracket squared, which almost always means that we'll use complete the square. So how do we complete a square? We want the x squared term by itself. So take out the factor that is in front of the x squared. Regardless of how unpleasant it makes the rest of the algebra, always take out the common factor in front of the x squared. In this case, it doesn't look too bad. Then we are going to take half of the number in front of x. It's going to be minus 2. We're going to add plus or minus, or sum in plus or minus that squared. that is going to form a perfect square for us. This rule, by the way, comes directly from the method that we use for squaring out a bracket. So if we start with a perfect square, a bracket that's going to be squared, we square the first by the second, and double it, and then square the second. Well, if we're doubling it here, halving this, and then squaring it is going to give the number on the end. So it's the same rule as multiplying out a bracket, squaring out a bracket. Just put in reverse. So I've added and subtracted in my squared term. I'm always going to be adding in the squared term because a perfect square always has a plus something squared. I've left this as -2 to be squared instead of just writing 4, because when I break this up into the perfect square that it now is, I need to remember that it is x minus 2 to be squared. So by not squaring out this bracket here, I'm able to keep track of what I should end up with. 6 on, this is my perfect square, x minus 2 to be squared, minus 4 plus 5 greater than 0. This just ends up adding up to plus 1, so we end up with 6 on x, multiplying in this bracket, we end up with 6 on x minus 2 to be squared, plus 6 is greater than 0. Now, the smallest thing that can come out of this part is 0. When x is 2, this is going to be 0. So this is always going to be greater than or equal to 0. For any other value of x, we're going to end up with some number squared, which is going to be bigger than 0. And then we have that plus 6 is obviously a constant. It's greater than 0. Therefore, the combination of the two must be greater than 0. So at the end of a question like this, we are going to write down that we understood what we were doing, because this is essentially a proof. For all values of x, where x is an element of the real numbers. Now, just to highlight that link again, this is basically identical to when we would be asked to do proofs of inequalities in algebraic work. So this is essentially the same question phrased in a different way, where we have to do a bit of differentiation first. But it's exactly the same idea as we would have covered when we were looking at proofs of inequalities. And that is what we need for looking at tangents and increasing and decreasing functions.